So let's imagine that we have a pendulum. So that's the ceiling, and we attach a rope of length L to the ceiling, and at the end of that we have an object of mass M hanging, and such that it always makes an angle, say theta naught, with respect to the vertical, and this object is then rotated. So it's rotating in a circle like that. So if we looked at it sort of edge on, then it would look to us something like that. So it would be rotating, it would be moving back and forth this way, because if we look further up, we see that it's rotating like that. So it's going in a circle. And so let's see what kinds of relationships we have between the forces and the accelerations. So let's do a free body diagram on this object. So let's ultimately try to figure out what is the speed of this object. So it's going in a circle, it has some speed here. All right, so here it's either it's coming out or it's going in. If we're having it rotate this way, then here the speed is directly out. And we want to know what this speed is. So we have the mass, we have the length, and we can do a free body diagram. Here is the object, and we have a tension in the string this way. Right, so there's tension there. There is the gravitational force mg pulling the object straight down. And so we need to decompose either mg into a frame that has a tilted vertical and a tilted horizontal, or decompose t into a vertical and horizontal. And because of circular motion in this direction, the easiest thing to do is to decompose this one into the vertical and horizontal frame. And so the free body diagram ends up looking like this. We have not t, but right, the angle here is theta naught. So we have that the vertical part, so maybe we can do a little triangle there, and that's theta naught. And so the vertical part of that is t cosine of theta naught. So say we don't have t is the tension that's not given. It's going to come from the balance of forces. In this direction we have mg, and then if the configuration looks like this, then we have, well, let's to avoid negative signs given our convention, let's imagine that the thing has rotated and now it's in this position. So the tension looks like that. So we have the tension force like that. We have mg like that. And this angle is theta naught, right? Because the angle with the vertical is always theta naught. So we still have t cosine theta naught in the vertical direction. But now the horizontal part of this is this way, and it's t sine of theta naught. So, right, sum of the forces, ma equals sum of the forces for the vertical and the horizontal. What does that look like? Well, in the vertical, we have ma, so we want to write ma equals sum of the forces, or the total F, on the right-hand side. So for the vertical, we have, right, the forces side. We can see the two forces. It's t cosine theta naught, and ng is downward, so that will come in with a minus sign. Then the left-hand side, the acceleration side, we have to figure out how it's accelerating in the vertical direction. And it's not accelerating in the vertical direction, so this must be 0. And then in the horizontal direction, we see that we have one force, so we have t sine of theta naught. So clearly the acceleration in the horizontal direction here cannot be 0. And of course this is circular motion, so the conditions for circular motion apply, and so the left-hand side is really the mass times the speed, that's unknown v, that we want, squared divided by the radius. What is the radius of the circle? Well, it's L. So if this length is L, then this has to be L sine theta naught, and so we divide that by L sine theta naught. Those are our two equations. And so this equation will give us the tension, right? So this one will give us T is equal to mg over the cosine of theta naught. And then, so we can replace this T with known values, and we can solve for V. So the V is equal to L T, let's just write it out, then we'll replace it. L times T sine squared theta naught divided by the mass and square root, right, because this is V squared. And so that is L, T is this, so we have mg over the cosine of theta naught. Then we have sine squared theta naught over m square root, which we can simplify. And let's bring it over here. Well, let's just come back up here. And so we'll get that v is, the m's will cancel. We have a sine squared theta. We could write that as 1 minus cosine squared theta square root, but let's just 1 minus cosine squared theta naught, but let's just leave it like that. So this is the square root of g L sine squared theta naught over the cosine of theta naught.